Okay. Our next speaker is Katie Crotts. Feel free to share your screen, Katie. So Katie will talk about follow-up exploration of TWA7 planet disk system with JWST NearCam. Whenever you're ready, Katie, take it away.
All right, perfect. Can you hear me? Yeah, yes,
Yes,
I
we can
can.
hear you. Yes.
Okay, perfect. Thank you. All right. I just want to again thank the organizers for letting me give this talk online. Apologies for not being there in person, but I'm still excited to talk about some recent research that I just recently published looking at the TWA7 system with NearCam. And just shout out to my co-authors who helped make that work possible. All right, so my the previous speakers already gave a good introduction to debris disk, so I won't go over it again in for the sake of time. But I did just want to show this diagram here or illustration, kind of showing this example debris disk exoplanetary system. So, similar to our own solar system, debris disk can have multiple different components, including the asteroid belt and Kuiper belt analogs. But for this talk, I'm going to be focusing on these cold Kuiper belt analogs that we can easily directly image and resolve. And of course, we're also interested in the planets in these systems, where we expect that there are likely these uh, planets that are on the edges of their solar system that are interacting and sculpting their debris disks. And we have some evidence to back this up. So, the more debris disks that we image and resolve, the more that we see that they all kind of host a wide variety of morphologies, rings, gaps, warps, eccentric disks, etc., that support this idea that planets are directly interacting with their disks and creating all these different types of asymmetries and substructures. But there is one problem with this idea, and that's the fact that in most debris disk systems, we actually don't see any planets. Um, so there's a couple, but again, in most systems, we're not detecting any planets. And the reasoning for this could be the fact that even Earth mass planets can effectively carve their disk because they're low mass and optically thin. So this suggests that perhaps um, we're just not sensitive enough to these lower mass planets that are in these systems than with direct imaging currently. So this is kind of where JWST comes to our rescue, as it's the instruments of JWST are really pushing the planet masses that we're sensitive to, getting into kind of the sub-Jupiter regime. And there's a lot of different surveys and geo programs that are taking advantage of this. So one being the Sub-Jupiter Imaging Survey, that's PI'd by Aaron Carter. So this particular survey is looking at the TW Hydra system and is the goal is to essentially search for these sub-Jupiter mass planets that previous to JWST we weren't able to image because we just weren't sensitive enough. So this is a so I'm showing here the detection sensitivity for this particular survey. And again, you can see that we're really pushing below the lowest mass image planet to date and getting it into that sub-Jupiter mass regime. And the separations that we are separate or that we're sensitive to are the same kind of separations that we are detecting debris disks. All right, so one of the observations that were a part of this survey was on the target TWA7. So this is a young M dwarf. And we've actually have known about this system for a while now because it harbors this very bright but complex near face-on debris disk that has essentially been imaged since the late 90s with a bunch of different instruments. Um, and as you can see from the sphere polarized intensity image, there's a bunch of different substructures, um, including three different disk components. But what I want to focus your eye on is this narrow ring that sits between the inner and outer disk components that almost resembles this like narrow ring or this resonant-like structure. And the authors of this data also thought similarly. So they compared the morphology of this ring with N-body simulation work that's been done previously, looking at disk-planet interactions. And they basically hypothesized that a planet that's in this underdense region of this narrow ring could essentially explain the disk morphology. So fast forward to 2024, where this system was imaged with MIRI. So I'm just overlaying that same simulation with the MIRI image. And what we find with this data is a bright point source at the exact location that a planet was predicted to be. And what's even more exciting is that we look at the photometry of this point source and compare with to upper limits from sphere. This point source is consistent with a Saturn mass planet. So really awesome discovery. If this is really a planet, this would be the lowest mass planet directly imaged to date and is really the first, real Saturn analog. All right, so of course that's not the end of the story because I'm here to talk about our near-cam observations. So I'm showing the 2 and 4 micron data where you can see the disk is imaged quite nicely. But of course what we're really interested in is whether or not we see this planet candidate within our data. So at 2 microns, we're not seeing anything but the disk, which is what we would expect for a planet companion. But at 4 microns, there is potentially something there. So here I'm just putting the MIRI data right next to our 4 micron NearCam data. And when we subtract a best fit disk model from our 4 micron data, we do find a significant residual at the same location as the candidate image with MIRI. So we don't detect it very strongly. So by itself, one might not think much about this residual, but considering the point source image with MIRI, we do believe that we are seeing this same companion. All right. So when we include our near-cam photometry with the MIRI photometry and upper limits set by sphere in the 2 micron data, we find that this object is still consistent with a Saturn mass planet rather than a background object such as a galaxy or brown dwarf. So really exciting that we can further confirm this being a planet candidate. And if this is a planet, we can also say something about its atmosphere, where we need a warm Saturn mass planet with above solar minimalisty and a chemical disequilibrium to explain our photometry. So I think I'm running out of time, so I just wanted to go back to connect the planet to the disk substructure. So again, we see this underdense region in the resonant ring. If we measure the azimuthal surface brightness across that ring and measure it across all the different observations from the late 90s, we do find that this ring has a Kepler-like rotation expected for a Saturn mass planet at that location. So this further suggests this candidate being a Saturn mass object. All right, so I'll end with future work. We just got some ALMA time accepted for cycle 12 to observe this disk at higher resolution. And we're also planning on submitting a cycle 5 proposal for JWST to try to characterize this planet further with near spec. All right, so I'm out of time. I'll leave my summary here. And I just wanted to promote that I am on the job market again this year, or looking for a postdoc for next year. So if you're interested in this work, please reach out to me. All right, thank you.
Can anything be said about TWA 7b, and specifically about whether it has migrated based on the structure of the disk?
Yeah, that's a really good question, and I don't think that's really been looked at in depth yet. There has been some N-body simulation work just kind of basically taking the disk and then inserting the planet in. Um, and that is able to replicate that three disk component structure. But that's something that I think would be very interesting to look at to see if we can say anything about whether the planet has migrated or not.
Okay, another question? Okay, I'll use my host privilege to ask another question. So from your experience with daily high contrast imaging, do you think going to longer wavelengths for cooler planets would be more effective strategies going forward with looking for these planet candidates?
Yeah, that's a really great question. I have a colleague who has looked into this, and at distances, I think like within 35 parsecs or something, Miri is actually maybe possibly the better choice for detecting these colder planets. But once you get to kind of farther out than that, then NearCam is still kind of the best option. But definitely, I think that Miri should be considered um, when looking for these cold planets in nearby systems for sure.
Yeah, thanks for sharing that. Okay, are there any questions online? Okay. All right, if there's no more questions, let's thank Katie again.